Alright, so Thevenin, we're going to keep our original 50 volts. We're going to get rid of R1. A, B is right there. Okay, so now I'm going to solve that circuit. I'm going to solve that circuit just like that with the load removed. And the max voltage between A and B is going to be Thevenin. And so if I pop that load out of there and measure it while it's working, I will see on my meter Thevenin. So let's go ahead and I'll show you kind of what I do, or at least what I'm thinking when I do these. So let's just declutter that circuit. So let's draw our original circuit. Okay, there's our 50 volts applied. I'm going to show A, but I'm going to leave that load right out of there because I don't care. I don't even want to look at it. R2, R4, R5, and B is right there. Okay. Okay, so now what I need to do is figure out, well, what is the voltage that I would measure if I put my meter in on point A and B just like that. Red lead on A, black lead on B. Alright, what number am I going to see if I just went in there and measured it? Okay, so looks like I forgot something, interestingly. Okay, that'll mess you up real bad. So R5, now this is going to be R3, that's what I forgot. Okay, so let's get rid of this and put it more cleanly. Alright, so try to write clearly and cleanly, because when you're going and looking at things quickly, especially on if you're under a time crunch, it's super easy to make mistakes, and the time crunch just makes it even more likely that you're going to make a mistake because you're trying to rush. But that's, that's practice how you play, right? Okay, so I'm going to simplify this circuit because it may not be, super obvious what's going on here. But I see my meter there. I'm just going to simplify this circuit. Now I'm going to draw just a vertical redraw showing R2 in series with a parallel network that hopefully will be more clear here in a second. So I'm just going to show my power supply. Okay, this is going to be my Thevenin redraw that I'm going to work from. Okay, so R2. Okay, and then that's going to be a parallel network. And on one side, I'm just getting to my negative side of my battery now. On one side, I've just got R4. Okay, and on the other side, I've got R3 and R5. Okay. So just want to see what's happening. Where is my current flowing in this circuit? Where is it splitting? Where are my voltage drops? And most importantly, where did A and B go? Well, A is here, B is way down here. Okay, so look at this. Basically, the key thing that I need to see here, I might erase this in a second, but just to show, here's my positive lead, here's my negative lead, alright, or my black lead. So the voltage that I care about is that R2 and R3 voltage. The other ones I don't really care about unless I'm planning to double check my work here, and I probably should, just so you can feel comfortable with that. Alright, so now I'm gonna solve this circuit by itself. I'm gonna scroll up so I can't see any of my other stuff because I don't even want to look at it while I'm doing this, because there's just too many opportunities to grab the wrong value. Now I just gotta make sure I grab the right values here. 1K and R5 is 3.3K. Okay, so I'm talking this out, so hopefully as a beginner, it might take a little bit longer to solve this or to see these things. As I'm talking it out, just try to beat me done. If you can beat me done, then you got it. Okay, so here's the circuit. I don't care about anything else in the rest of the world doesn't exist. I'm just going to solve this little circuit all by itself. Okay, so I'm just looking at this little circuit, this little redraw, my Thevenin redraw. And Thevenin, when I'm done with this, is going to be VA to B. Alright? Okay, let's just solve this baby. So I have an REQ, which consists of R3 and R5 in parallel with R4. So let's just do that. Okay, so REQ, okay, is 1 over, and I'm just going to write it out. R3 plus R5 down under here, okay? Because it's the sum of that branch in parallel with R4, okay? 1 over R4 this time. Okay, so that's going to be my REQ. Let's write it in some numbers. Okay, 1 over, and I'm just going to write it out again. Oops. Just very carefully writing it out so that I don't make too many mistakes. You know, I know that typically when we do this, you know, we're trying to hurry and get it done within a time limit. If not, I recommend that you do that because it'll actually help you to work a little bit better under pressure. If you don't apply any pressure, then how do you know how you're gonna act under pressure? Well, turns out you don't. Alright, so I'm going to wake up the old calculator and I'm going to punch it in just like that, but I need to verify what I punch in. So if your calculator doesn't show your equations when you punch them in like mine does, you should probably just write out all the steps, because you know, trying to find a math error without doing that is going to, you know, good luck. You're just basically starting over. Okay, so I'm going to punch that thing right in there. 1 divided by, get some parentheses on the subject here. Okay, 1 divided by another set of parentheses, because I'm going to say 1K plus 3.3K. Now I could have added those in my head, but you know, it's nice to have clean numbers, but that's not always the case. Okay, parenthesis 1 divided by, now I've just got one thing over there, 4.7 e to the third. Okay, and I'm going to verify this once I punch it in, and I've got a missing parenthesis someplace. Clear. I don't escape. What do I got here? All right. Well, let's just add another one, see what happens. All right. So here's my equation. Now look, it matches. So I've got 1 over that plus that, which is exactly what I wanted, plus 1 over that. Okay, so that's kind of all the double checking I'm going to do for this number, at least for now. We'll see if I make any mistakes. Okay, so 2.246 k ohms is my REQ. Now that's in series with R2, so our total for this circuit is going to be R2 plus R equivalent. Alright. R total equals R2, which is 1.8. Now look at that. Easy mistake. 1.8 k ohms. So write down all your units. It's so easy to grab a wrong number and then you're messed up. Alright, plus, and don't multiply, plus REQ, which we found to be 2246 ohms, minimally, or rounded to 4 digits. So RT equals, let's bring the old calculator, and I do have that number. Okay, so let's just do it just like I've written it, 1.8 e to the third plus my less rounded number is going to be 4.046 k ohms, all right, or just 4,400 or 4,046 ohms. All right, now we can find current. I'm going to switch colors just because this is going to start getting a little bit busy and I want to stay organized. So I'm going to do my currents over here in red. So I total is going to come that way, right? IR4. Oh, here's one I want. I'm going to call that IR3 because that actually is the resistor that I care about. If you remember, R2's voltage plus R3's voltage is where I'm going to measure my A to B voltage, or at least mentally measure it, I guess. So IT, whoops. So R2 is going to see I total, and this branch is going to see basically R3 and R5 are going to have the same current. I'm writing it as R3 because R3 I've got my eye on. I'm going to find R3's voltage and R2's voltage at a minimum to move on to the next step. So let's go ahead and do it. Okay, so I total equals V total over R total. Ohm's law. ABCs of electronics, right? 50 volts, my original voltage, okay, over RT for this circuit, which was 4046 ohms, provided I didn't make any mistakes. So far so good. It looks okay as long as I've written everything down properly. Okay. All right, so let's just bring the calculator in and solve that one. Okay, so let's do it. Where are you, calc? Where are you, TI-89? So if you own the ROM for your TI, or if you own a TI-89, you can basically go to TI's or Texas Instruments website and get a ROM, or you can pull they'll show you how to pull the ROM off of your calculator if you have a lot of settings you like. And then you can use this TI-89 app on your phone, which is nice. So 50 volts divided by 4, let's just go use our less rounded number right here. Okay, so I got a current. So the current total should be 12.36 milliamps. So I've got my phone displaying in its own little window on my computer. And on my phone I have my calculator. So the app I'm using to show it on the computer is called Visor, which is kind of a cool app so far. I like it. Anyway, so there's my I total. So now I can find the voltage. I can find the voltage of R2. Let's just go over here in green. So VR2 equals I total times the value of R2. Okay, so VR2 equals 12.36 milliamps times R2, which was 1.8K ohms. So VR2 equals, let's just see what it equals. Okay, so that current, which was found, that looks right. Okay, that current times R2's value, which is 1.8K. Alright, so I'm getting 22.25 volts. Alright, so far so good. So now I'm just going to use Kirchhoff to find the voltage of the equivalent network, or R4, or whatever you want to say. So the voltage of REQ equals V total minus VR2. Alright, VREQ equals 50 volts minus whatever we just found, which was 22.25 volts. So VREQ equals, alright, let's get the old calc back. Oh, come on, calc. Okay, clear. So 50 volts minus that voltage that we found for VR2, less rounded, minimally rounded, 27.75 volts. So basically Kirchhoff is telling us that the parallel network has that because that's all that's left over. So if I add those back together, they should be 50. So far so good. If I haven't made any mistakes, that should be fine. Now I need to find the branch currents. Okay, so the one I really care about, is IR3. IR3, because that's the one that R3 voltage is part of my AB voltage, which is my Thevenin, which is the whole point of why I'm here. Okay, or at least here doing this right now. Okay, so IR3 is going to be, let's see, now I've got to say V R equivalent, right? And then in that branch, right, this branch, I've got a sum of resistors. Well, that's going to be R3 plus R5. Okay, let's look at it. IR3 equals, don't just write the same thing again. 27.75 volts over 1K plus 3.3K. Alright, so in my head I know that should be 4.3K. I'm just going to plug it in just like that so we can see it. Alright, I just want to see that happening. Alright, so that voltage that we found before divided by the sum of the branch resistance, or the branch resistance itself. Okay, so 1 e to the third plus 3.3 e to the third. Okay, so just being pretty detailed about it. So 6.454 milliamps. All right, so that's what my calculator shows. All right, now I have an opportunity to double check here. So if I found the current for R4, which I will, so basically it's that divided by R4's voltage, 4700. Okay, that current added to our other current. Okay, let's look at it. So let's clear this. So if I add these two currents together, basically that's going that way, that's going that way. That should sum to be I total, just a little Kirchhoff node analysis. And we use that as a double check right here. Come on. Hello. Plus. Alright, so it did come out to our total current. So I feel pretty good about that. I don't think I'm going to do any more double checks unless I make a mistake and have to come back through here. I'll start doing those double checks. So now let's just find V R3 right now. Alright, so get back on some green, do a voltage down here. Okay, so V R3 equals IR3 times R3, so this should be easy. Okay, VR3 equals 6.454 milliamps. Okay, remember that's 10 to the minus third. Okay, times R3, which is 1K, 10 to the, whoops, let's just write it out, come on now, which is 10 to the third. So basically you have 1, the 10 to the third and the 10 to the minus third cancel. So that should just give us VR3 equals 6.454 volts. Alright, so I kind of got a little crunch down in there. So here's our voltages that we care about. Okay, right here. Oops, I didn't get, let's get a red or something here. Not red, still not red. Okay. Okay, we care about that voltage, and we care about that voltage, right? Because our meter's going to be in here like this. On A and B, minus plus, right? So that voltage we see between there, R2 plus R3, is going to be our Thevenin. So let's see, I'm going to come in here, maybe let's try orange. Thevenin equals VAB, right? And VAB equals VR2 plus VR3 3 VAB, well, we got 22.75 plus 6.454. Right, now I'm looking here and here, down here in this messiness. Okay, so VAB equals, let's just do it. Let's do the calculator. All right, let's see what happens. Clear. All right, so let's see, where did I leave off? Okay. Enter times 1K, right? So I did that in my head, so I didn't have a less rounded number in my calculator. Plus 27, where's that? Less rounded. 27.7, did I say 75 or 25? Oh, look at that. I may have made a mistake. Nope, that's that one. There it is. So that's why keeping everything in your calculator is probably not a good idea either. Just write that stuff out. Write that stuff out so you can see it. 28.7 volts. Okay, that is our Thevenin number that we care about. Okay, 28.7. Let's go put that on our 28.7 volts. Let's go put that on our equivalent circuit right now. Okay, Thevenin equivalent circuit. 28.7 volts. So let's just make sure I didn't write that down wrong, which I do often. Okay, I'm gonna scroll, apologize for that. Okay, so there's our Thevenin number, 28.7. Okay, 28.7. Okay, ready to solve for our Thevenin circuit. All right, now this is taking quite a while because I'm explaining as I go, so hopefully you may have already beat me done. I hope so. I hope you were trying to beat me done. Alright, let's see here. I'm going to come in here with blue, and I'm going to solve for our total of this little circuit, which is going to be R Thevenin plus R1. Our total equals 1356 ohms plus 2.2k ohms. Our total equals, well, what would that be? 3556. Well, let's see what the calculator says. Okay, so R Thevenin 1356 plus 2.2 e to the third, and I think my mental math was okay. I don't even remember. 3.556k ohms. All right, well, there you go. Now I can find that current. I can now find this current, the current my R1 would see in my original circuit, IR1. All right, so IR1 equals V Thevenin over the R total for this little guy. Okay, IR1 equals V Thevenin, the most voltage available to the circuit or to the load would be 28.7 volts over that number 3556, which was our total resistance in this little guy, this little circuit. Okay, remember I'm doing it on a clean sheet on purpose because I don't want to mix my values or try to confuse different circuits in my head. Alright, so let's just find that number. Boom, boom, boom. Clear. Alright, so let's do it. So let's see. V Thevenin was that number, minimally rounded, divided by a more rounded 3556 number. Okay, as long as I got all that in properly, I've got 8.071 milliamps. Okay, so far so good. Alright, so now I know the current of R1 and I want the voltage of R1, so let's get that voltage in here. And this will be the voltage and current of R1 in our original circuit, R1. Okay, VR1 equals IR1 times R1, Ohm's law again. Okay, 8.071 milliamps times, what is R1? 2.2 K ohms. Whoa, that went crazy. Alright, okay, so VR1 equals, bring the old calculator in on this. Alright, clear. So that number times 2.2 e to the third equals 17.76 volts. Alright, okay, let's get, so these numbers, this number and this number are going to be our voltage and current for R1 in our original circuit. So I'm going to take a second and transfer those numbers over to the original circuit, and then from there I think we can just use Kirchhoff. Let's see what we can do.